So we're still doing the part of like some chemical reactions, different part, like, different type of the chemical reactions. So for example, we started learning about combustion reactions, acid and base reactions too, and last week we started learning about metals reactions. Today we're gonna learn about something about solubility. So let's consider about what I mean by solubility. I mean, like, think about the word soluble or insoluble or soluble. When we say soluble, it means that it can be dissolved. It means it can be dissolved. Can be dissolved. That's how we can interpret that on the solubility too. So, in terms and if something we need to if we have something that we want to dissolve in, we need to have something that we want to dissolve in. This is called the solute. Put that into the solvent, producing that final product of the solution. The easiest method to understand the point is, for example, we have solute, bring like a salt, put that into the solvent of the water, then making that into salt water. Okay, so solubility rules, also known as solution chemistry, is all about like how we make a solution too. So showing you that this is a solution now, copper sulfate. Now we can see more things kind of coming out. The precipitate, can you see that underneath? There's a black chunk is coming out from it, indicating that there's more of those precipitate formed. But this is the copper nitrate solution that I prepared that with copper. Copper sulfate, this kind of solute, kind of salt, put that into the water, making the solutions form. That's easy as that, okay? So in terms of state, generally, when we talk about the solute has a state of the solid, more likely. Solvent are generally used in a liquid. Solution now is forming the state of the AQ, which stands for the aqueous. So whenever you see the AQ in the symbols, that's representing that this is a solution of something. Okay, so today we're going to learn about then what makes that precipitate, solvations and that. Okay, so don't worry about the precipitation reaction. Page 85, please. Yeah, I'm not going to talk about too much details about covalent bondings and bondings today. Let's make it fun, okay? Let's make it really simple. Just a few things you need to memorize, first of all. There are SNAPs rule you need to memorize. So SNAP stands for sodium, nitrate, ammonium, acetate, potassium. Let's write it down again. Sodium, nitrate, ammonium, acetate, potassium. We call this SNAP. So sodium, Na+, nitrate, NO3-, ammonium, NH4+, acetate, CH3, COO-, potassium, K+. These are the ions that they never form the precipitate. Precipitate isn't like they never form that solid. Forms solid or during the reactions. So for example, when we have a sodium chloride, for example, sodium chloride, as soon as you see the sodium and chloride in that, they would not, okay, we can have the solid like after evaporating like a salt, but they would not have the solid state, more like aqueous due to the presence of the sodium Na there. Okay, same for the nitrate. Any nitrate doesn't matter, like a lead, nitrate, lead to nitrate. As soon as you say, oh, I have a nitrate given here, then means it will not form the precipitate. It will come in the AQ all the times too. So that's giving you that AQ state all the way. Same for the ammonium, that NH4, say Cl, ammonium chloride. As soon as there's the ammonium there, the state must be AQ as well too. Go for one more, okay? Acetate, sodium acetate. really commonly used. You see that both of the sodium and acetate from this in the snap, that means it will come in the aqueous state all the times too. Some exception is when we evaporate. I'm not talking about when you evaporate the water. I'm talking about when they put it into the water, they will be dissolved in that 100%. But there are some that metal and non-metal combination would not be dissolved. So I showed you one example here. Can you write it down? The reaction between, first, count the reactants of silver nitrate, AgNO3, plus calcium chloride, CaCl2A equals here there. So this is what I mean by silver nitrate solution here, calcium chloride solution got ready in here. So I show you what happened and I put it into the conical flask. Probably show you the last year in the lab. Start with the calcium chloride. What you see there from the calcium chloride is this is clear. There's no color whatsoever. Okay. Now let's see what happens if I put some silver nitrate in it. See that? Okay. You will start to see some chunk, some like white. It's getting milky. It's actually, in fact, we can see some solid. Can you see that underneath the conical flask? I'll show you that. Underneath here. You see, look, it's on the chunk. These are what we call the precipitate. You will see that some colors of precipitate, like this kind is white. That means you got to think about what makes the precipitate from from what reactants. So let's have a think about it here. I just explained nitrate would not form any precipitate, any combination nitrate. And mixing these two up means that they are swapping their metals and non-metals, swapping their partner. So the possible exchange between the silver nitrate and the calcium chloride is that we can have something for silver is taking the chloride, becomes the silver chloride, and we can have calcium taking the nitrate. This is called a double displacement reaction. Calcium with the nitrate, given here like this. You may balance that by times 2 over here and times 2 of the silver nitrate too. Then let's write it down the state. Whenever you're dealing with the snap, it forms the aqueous. It always comes the aqueous state. Simple as that. But as you from the observation you had here, you actually see that there is the white chunky precipitate form too. If this is not from the calcium nitrate, this must be from silver chloride. So how we write that? We write the solid as go. This is known as the white precipitate. Okay, so kind of you see some merged kind of precipitate formed underneath of that too. So solution chemistry or solubility rules basically determine that what kind of when do we get this some precipitate from what reaction to what. So page 86 shows that solubility rules, also known as the solubility tables. This explains you like what forms a precipitate, what forms not. So you have a two table, table 1 and table 2. Remember that. Table 1 and 2 has quite a different too. So what we have in table 1 is these are the soluble in the water. Okay, this means most chloride, bromide, nitrate, or those ammonium, sodium, acetate, sulfate, they are soluble. Think about what you mean by soluble. Soluble means when something is soluble, that means that there's no precipitate formed. But when we say insoluble, or say sparingly soluble, or the slightly soluble, you may see that there's a precipitate formed. So for example, again, chloride, most chlorides are soluble, bromide and iodine as well too. But exception is, we have a silver. When these are combined with the silvers and the lead, they are known to be an insoluble. So it means that that table column here, it shows you that these are the form of the precipitate. Does it make sense? Okay, this is the exception of those solubles. Now, there is no exception for the nitrate, ammonium, sodium, potassium acetate. Did we learn that before? These are the snaps. So this means they will not form the precipitate at all, so they will always go for the aqueous state. Most sulfate are soluble except tin, barium, and the lead sulfate are not soluble. They form the precipitate. Some exceptions, slightly soluble. Lead chloride, lead bromide be slightly soluble. So it wouldn't be like this silver chloride. Like you cannot like you'll not definitely see like white precipitate as a silver chloride as this. But you would actually see that it's getting a little more murky. So color change a little bit happen too. That's a sign of the precipitate form as well too. Even though we don't see actually chunky parts of the precipitate. Again, no exceptions for those nitrate or the snaps. Calcium sulfate, silver sulfate would be the slightly soluble as well too. Means that there's a chance of that we're seeing some precipitate. But that really depends on what concentration you're using, but you don't have to really know about this yet. Okay. Second, you have a table 2, which is showing you all insoluble in the water. So think about what I mean by insoluble in the water. That means that these are the form of precipitate. So most hydroxide or the combination metal hydroxide will be insoluble, form the precipitate, except sodium, potassium, barium, ammonium, and silver. They are soluble, which means what? There will be no precipitate formed. Some exceptions, slightly soluble. There's a chance calcium and the tin maybe show some signs of this on the precipitate, but not as much as on the top. Carbonate was known to be most insoluble, forms of insoluble precipitate, except this sodium, potassium, ammonium, and no exception was slightly soluble. Phosphate would be most insoluble, means form the precipitate, except combined with those. What are those? Sodium ammonium, potassium, which are the snaps. Okay, sulfides are mostly soluble, insoluble, except again sodium, potassium, and ammonium here again too. Does it make sense, Joel? Okay. So why do we need to know about this? Okay, I will not ask you to memorize this. Don't worry. Okay. Instead, I give you a new cheat sheet given on your formula sheet here. Can you see that in the data sheet? This is your chemistry formula sheet, and you get an HCC. In here, solubility constant value there. Okay. Everything there are insoluble. Yeah, don't worry to memorizing any of those. Just need to memorize a snap, and if you need help, you can use this. You can use that to determine whether there will be a precipitator form or not. So, how do we use that table, or how do we use the snap rules to figure out? Let's have a look at some exercise there. Page 87. Is barium sulfide soluble or insoluble in the water? So again, the first method you can do is, if you're really most likely provided the solubility tables. So let's use the table given over here. You're given barium sulfide. So have a think of like in a barium sulfide. We know that most sulfides are insoluble. But do we have any exception in that? The barium. Okay, so barium sulfide is not in the exceptions of the insoluble table. This means what? Is insoluble in the water. Okay, only those are soluble in the water. Remember that I have a two table, table 1 and table 2. If you have something on like chloride, they are most likely soluble, except these. Table 2, they are insoluble, except these. Which means barium sulfide is mostly uninsoluble, except the sodium, potassium, ammonium. So therefore, barium sulfide we can just define as insoluble too. Does it make sense? Okay. Or we don't have a sulfate here, so we can use a sulfate for this table there. Next one, B, is ammonium phosphate soluble or insoluble in the water? What do you think? NH4, ammonium sulfate, phosphate. This is ammonium phosphate. It's a soluble. How do we know? You can either use the SNAP, or let's have a think about the phosphate. Most of the phosphate are insoluble, but we have an exception of the ammonium sulfate given here. So this is soluble. Or you can use the SNAP. It's ammonium part of the SNAP. Yeah, so we can just think, oh, it's part of the SNAP, so SNAP never forms a precipitate, it always comes in the aqueous form. So this means it comes in AQ like this. Too easy thinking about that, okay? Just using the table of SNAP rules, okay? So let's have a think about this. This is actually what happened between, this is kind of pretty. If I pour in kind of lots of the sodium chloride, this is actually where you see the precipitate. So color changes. This is basically due to some solids starting to forming inside of the mixture between two. Don't worry about how this source is formed. I'll probably explain that later next week. So let's go move on to the question there, 6.3. What precipitate, if any, will be produced when solution of the potassium hydroxide and lead to nitrate are added together? Okay, Ellie, can you write it down the reactant side first? Can you write it down potassium hydroxide and lead to nitrate? Because we memorize all the valences by now. And this is one of the reasons why I've been like emphasizing and pushing you to memorize all the valencies, because you won't be told that what the hydroxide, what the nitrate is from now on. So the way we can write that is solutions of the potassium hydroxide can be written as KOH. Solution of the lead 2 nitrate, PB, NO3 to straight away. Okay, lead 2, PB, and NO3 is 1 minus. Okay, now, if these two go through the reactions there, let us just think about what's going to be happen. Okay, there will be some reaction between, if they're swapping their partner, you're swapping their non-metals, there will be a chance of their forming lead hydroxide. Okay, the chance of the potassium nitrate will be formed. Oh. Let's not write it down the state here yet. Okay, we can balance that having the 2 hydroxide and two required, and this is now balanced. Okay, now rule number 1. If you remember SNAP, you remember the potassium and nitrate is part of SNAPs, then you know that potassium nitrate will never be a solid. Therefore, it's a state of the AQ all the way. Now, it's time to determine that whether this is forming the precipitate or not. You have 2 methods. If you're provided the table in the page like page 86, you can use that table. So you can either find the lead or the hydroxide. Let's go with the hydroxide there. Hydroxide in the table 2. Most hydroxides are insoluble. They will form the precipitate, except these over here and the calcium in the tin. Can you see any lead hydroxide in the exceptions? No, which means lead hydroxide most likely be a precipitate in the solid state. There's the one method you can use. Second method, use that table. Can you find the lead? And can you find the lead hydroxide on the list? You do, proving that this is a solid. Does it make sense? Okay. I'm not too sure whether you provide this formula sheet. I hope you do. If you do, just use that. If you're not, you most likely be given these solubility tables, because up to year 10, we don't really ask the student to memorize solubility table yet. We'll probably do that in year 12. Okay. Okay. Could you try the next question, please, then? What about the sodium sulfide and copper 2 nitrate? Okay, shall we? Sodium sulfide Na to S aqueous. This is reacting with copper to nitrate, which is Cu nitrate NO3 and to aqueous there. Yep, there's nothing really hard about this. If these go through the reactions, then you'd expect to have, there will be a copper sulfide, CuS, something we don't know yet, and we get the two of these sodium nitrate reformed. Now, as soon as you see the sodium in the nitrate, which is a part of SNAP, you just definitely know that, oh, the state-wise, it would be aqueous all the way. Does it make sense? Okay. Now, what about copper and sulfide? Sulfide is not being a part of in here. You can't really find the sulfide there, so you might need to use that copper sulfide from the solubility table again too. Page 86, going back to that page again. The most sulfides are insoluble except these: potassium, sodium, and ammonium. Give me a really easy clue then. Oh, okay. This is not part of the exception. This must be the solid then. Does it make sense? This is how that easy to use the solubility table and SNAP rules to figure out whether there'll be a precipitate or not. Now, from the A and B, copy this down to, thinking about the meaning of the AQ there. AQ means it's kind of separated and they're kind of involved with the water. So the way we can rewrite the K or H is, this can be written as K plus aqueous plus OH minus AQ like this. Okay, so AQ, the meaning of the AQ means that they are not really bonded, they're kind of actually separated form. So having two each means we have a two of that each here like this. Now that plus, lead and nitrate can be written in the same manner, so it means we have a lead 2 plus AQ plus that, there will be 2 NO3 minus AQ here like this. Now that's what we have on the reactant side. Can you see, like, I kind of separated this AQ into the different forms. Let's do the same for this side over here. Now, what you see there is, when they're forming the solid state, that means they're really rigid, they kind of bonded together really strongly. So I can't divide that. Means it will just comes as lead hydroxide solid. You might be questioning that, oh, hey, what's the difference between that and that? You need to look for the state. Something AQ means that it has been already separated due to the water. This is not affected by the water. This is why we call that they are insoluble. They don't dissolve or they're not interacting with the water. What about here? This is still reacting with the water, means that we still have 2 potassium ions and 2 NO3 minus ions from that. Yep, now, interesting things happen. Can you see, like, I do like a bit of like a mathematical approach here. I have 2 potassium on my product side. I also have 2 potassium on my reactant side. Mathematically, I can cancel them. Okay, same here, NO3, I can cancel these two, 1 here again too. Okay, then what you see there is, you do see that only left over here is then lead, aqueous, and 2OH minus aqueous that was forming lead hydroxide. See, after we canceled out those ions that didn't really get involved in the chemical reactions, we just got a pure reaction type. Can you just say, oh, this means like, oh yeah, we have a reaction of those from that net equation there. This reaction is known as the net ionic equation. The one on the top was known as the full equation. So to get the net ionic equation from the full equations, what you can do, you can cancel out on both reactant and product side that the ions that didn't get involved in the chemical reaction. Then you'll be questioning that, oh, that means should I write this every single time to write that? You don't have to. Just remember about this, what I talked about SNAP. Those SNAP will never form the precipitate. Those SNAP will always be in the aqueous form. Means that SNAPs can be cancelled. We call the snap as like a spectator ions that do not form their precipitate, or ions that do not get involved in chemical reaction. What do you mean by do not involved? There'll be a spectator. They'll be high up there. They'll be like a manager. They don't do anything. I shouldn't use that word, but okay. Yeah. Okay. Managers do something, by the way. Okay. Spectator isn't like they're watching. More like they're watching that like working, but they're not really involved in the chemical reactions. Just like over here, potassium nitrate is like they're just floating. They're doing pretty much nothing compared to like lead and hydroxide. So simply, what we can do, we can think from here that is, oh, if I cancel the potassium and nitrate over here, the leftover would be hydroxide and the lead, and we know that they're from the precipitate. So you just copy those down, and you finally get the net ion equation done. Then can you write the net ion equation for the B? You may follow this on the second method, the method I wrote in here, or you may just think about the spectator ions. We can try both. Okay, let's follow the first method there. Sodium Na2 sulfide means we have a 2 sodium aqueous and 1 sulfide AQ. This is reacting with copper 2 plus AQ and 2 nitrate AQ like this. Okay, leaving that, we have a copper sulfide as a solid, and having that 2 sodium 2 plus and 2 nitrate ions on the product side there. You actually can see that sodiums can be cancelled out, 2 of the sodium, 2 of the nitrate can also be cancelled out. Leaving that, we have a copper 2 plus aqueous when this is a react with a sulfide A2 minus, forming that copper sulfide solid like this. Simple ionic equation formed there.
Do you have to include like the plus and minus?
When you're writing the book, yes you do, because they are coming in the ionic forms. They're kind of separator forms there. We will have a chance to talk about why it comes as an ionic forms too, but today I'm just going to focus on like how to solve the questions. Okay, now could you try for the 6.4 there, please? I'll leave here. I've left this information here for like a few minutes, so you can have a look at that again. And you can also use the on your the solubility tables. Can you write the full equation and the net ion equation too? Just for both?
Also, you can rub it out.
Oh, nice. Okay. We'll try it without looking at it. Okay, challenge it. Finished? Okay, let's check. Write a full equation for the reaction between iron 3 nitrate and sodium sulfide. So let's start off from iron 3 nitrate, Fe, NO3 and 3, Aq is known as iron 3 nitrate. Reacting with the sodium sulfide, that's Na2, SAQ2. So I can just straight line like this AQ to AQ because both of them have sodium and one has the nitrate, the SNAP, so that forms the AQ all the times. Now when these two are reacting each other, like we can expecting that they're exchanging their partners, so what that means is you get sodium, that nitrate will be formed, and there will be iron 3 sulfide. to balance that iron 3, Fe2, SES3 is how you write the iron 3 sulfide. Okay. State-wise, let's balance that first. We need to have 3 of that at least, making that 3 and 2. Okay, that makes 6 of the sodium nitrate and having 1 each of that. Make sense? All right, sodium nitrate. As soon as you see that sodium and nitrate, you would know, oh, that's AQ all the way to the AQ. Now, iron 2 sulfide. If you look for your your solubility tables too, sulfide is mostly insoluble except the SNAP. Means that iron 3 sulfide is most likely be a solid there. This is the full equation. Okay, net ion equations. You don't have to write it down all the way. As long as you can see like, oh, we have a SNAP coming in here. You can just simply write it as, oh, I have a 2 iron 3 plus AQ plus that 3S2 minus AQ. That formed Fe2 and S3 solid here like this. Okay, I just simply cancelled out sodium and the nitrate, and then this is the result. Easy. Next one, copper 2 sulfate and the sodium hydroxide. Let's write it down. CuSO4AQ. This is reacting with sodium hydroxide NaOH. AQ again too. Now, copper sulfate is known to be a solution for sure, okay? Or you can have a look at your solubility tables or even that. You can actually find the copper sulfate in there. So that's the case of like, we have the that's the case that we have the aqueous forms. Okay, now when these start working to reacting each other, you would form NaSO4, Na2SO4 plus that CuOH2 like this. Balance that times 2 on the sodium hydroxide. This will balance the numbers on the reactant and the product side. Now, state of the sodium 2 Na2SO4 is, as soon as you use the sodium, it simply be AQ. The problem is the copper hydroxide. Now, looking back into your solubility tables, or you can use the formula sheet, the copper 2 hydroxide is on the list. Can you see that? Okay, means that's a solid straight away. Easy. Now, time to write it down, the net ionic equation too. So as you can see that, sodium and sulfate did not get involved in the chemical reaction. Okay, it's not all about the SNAP. Yes, sodium is a part of SNAP, but sulfate, we had it in the forms of the SO4AQ. We also have SO4AQ there. Does it make sense? It means we can cancel that out, cancel the sulfate. The only remainder would be the copper 2 plus AQ reacting with 2 hydroxide AQ, forming that CuOH2 solid there. This is the net ionic equation then. So pretty easy to how to write the net ionic equations once you understand the SNAP, or like you understand about those ions that didn't get involved in the chemical reaction that form they can be cancelled out of each other. Okay. Next week I will talk more about what the solubility is. Again, we're gonna finish the rate of reactions, chapter 7. There will be a short some kind of topic test about the solubility, but it will be very similar to what you had today. So basically, I just want to test that. I don't want to forget about how to use the solubility tables. You will also get this provided this table as well too. Make sure you know how to use it. These are forming precipitate. Make sense? Okay. Right. Homework for next week. It's holiday. Relatively short. Can I get the homework from last week too? Pretty long. Thank you. So, that's it for today. Okay. Make sure you practice a bit of that, especially net ion equations. I hope you learned that in school. I really do. Okay. All right. That's it.